I want to talk about a function called the hereditary base change that takes a number and often makes it bigger, usually much, much bigger. And once we've defined that, we'll define the Goodstein sequences, where we just alternate between applying hereditary base change and then we subtract 1. Then we apply hereditary base change and then subtract 1. And we go back and forth, and surprisingly, even though this hereditary base change seems to make numbers much bigger, subtracting 1 is going to win out. Eventually, these sequences all decrease to 0, but they decrease to 0 very, very slowly. And that's what Goodstein's theorem is going to say, that these sequences all decrease to 0. Before we can say what Goodstein's theorem is about, we need the idea of hereditary base notation. In ordinary base notation, we pick a base b has to be an integer greater than or equal to 2, and we write a number as a sum of powers of b. So ordinary mathematical notation is based on base 10. So when we write 102, that means 10 to the 2 plus 10 to the 0 times 2. On the other hand, in base 2, we would write 102 as a sum of powers of 2. So 102 is 2 to the 6th plus 2 to the 5th plus 2 squared plus 2 to the 1. And in base 3, 102 would be 3 to the 4th plus 3 squared times 2 plus 3 to the 1. And in general, when I say write a number in base b, I mean write it as a sum of powers of b, and each power can have a coefficient. The coefficient has to be at least 0, a non-negative number, and less than b. So this 3 squared times 2 is fine in base 3 notation, but if we had 3 squared times 3, we would say that's really a 3 cubed instead. In hereditary base b notation, the only new thing is that we also write the exponents in base b notation. So to write 102 in hereditary base 2 notation, we rewrite all the exponents. So the 6 becomes 2 squared plus 2 to the 1. The 5 becomes 2 to the 2 squared plus 2 to the 0, and so on. And in hereditary base 3, 102 is 3 to the 3 to the 1 plus 3 to the 0, plus 3 to the 3 to the 0 times 2, plus 3 to the 3 to the 0. In hereditary base 10, 102 doesn't change much. It's 10 to the 10 to the 0 times 2, plus just 10 to the 0 times 2. Once we've taken some number and written it in a particular hereditary base notation, we can then change the base while leaving the structure of the notation alone. So we could take 102 in hereditary base 2 and just change all the 2's to 3's, and that gives us a new number. It's 3 to the 3 to the 3 plus 3, etc. So every 2 becomes a 3. This is much bigger than 102. It's actually this long 15-digit number. This gives us the base change function. The base change from b to d of n, we write it with this capital B. The bases, b and d, are the subscripts, and n is the input. This is the number we get by writing n in hereditary base b notation, and then changing all of the b's into d's. For example, B23 of 102 is that 15-digit number we just saw. For a smaller example, just start with 15. In hereditary base 2, 15 is 2 to the 2 to the 1 plus 2 to the 0, plus 2 to the 2 to the 1, plus 2 to the 2 to the 0, plus just 2 to the 0. So B23 of 15 is 3 to the 3 to the 1, plus 3 to the 0, etc. Every 2 becomes a 3, and then if you calculate that out, it's 112. On the other hand, in hereditary base 3, 15 is 3 to the 3 to the 0 times 2 plus 3 times 2. So B34 of 15 is only 24. The idea is that this base change function makes numbers bigger, and it often makes them a lot bigger, especially once we're over certain thresholds. B23 of 15 is only 112, but B23 of 16 is this really long number. This hereditary aspect means hereditary base change makes a much bigger difference when your tower of exponents is taller. Now we're ready to define Goodstein sequences. The Goodstein sequence starts with a number n and keeps rewriting it in different bases. So we start with n in hereditary base 2, and in each step we increase the base by 1 and then subtract 1 from the number. And if we ever hit 0, we stop. So the Goodstein sequence starting with 2 continues to 2, because that's 3 to the 1 minus 1. And then 2 in hereditary base 3 is just 3 to the 0 times 2. So in base 4 it doesn't change. And then when we subtract 1, we get 1. And then when we base change 1 from base 4 to base 5, it doesn't change. So we subtract 1 to get 0. So the Goodstein sequence starting with 2 is just 2, 2, 1, 0. If we start the Goodstein sequence with 3, we write 3 in hereditary base 2. That's 2 to the 1 plus 2 to the 0. So the next element is 3 to the 1 plus 3 to the 0 minus 1, which is still 3. And the next element is still 3. And then we decrease by 1 each time. So the sequence goes 2, 1, 0, and then stops at 0. The Goodstein sequence with 4 looks a little different, though. In hereditary base 2, 4 is 2 squared. So the next element of this sequence is 3 to the 3 minus 1, which is 26. In hereditary base 3, 26 is 3 squared times 2 plus etc. So the next element is 4 squared times 2 plus etc., which is 41. And this actually keeps going for a while. It's not exploding, but it does seem to keep getting bigger. In fact, it keeps getting bigger for a long time before it starts getting smaller. It takes about 10 to the 10 to the 8 steps for this sequence to hit 0. So the Goodstein sequence starting with 3 was only 6 elements long. The Goodstein sequence starting with 4 is like 10 to the 10 to the 8. And as soon as we start the sequence with bigger numbers, this growth gets really astronomical. So this is what Goodstein's theorem addresses. Is it really true that the growth we get from changing bases is always eventually going to be overtaken by subtracting 1 at each step? And Goodstein's theorem says yes. Even though these sequences seem to grow very quickly, for every n, the Goodstein sequence starting with n eventually reaches 0. The plan for this series of videos is, first of all, to prove Goodstein's theorem. Then we're going to talk about this idea that these sequences really do take a long time to reach 0. We'll define a function. G of n is the number of steps it takes for the Goodstein sequence that starts with n to reach 0. Goodstein's theorem is exactly saying for every n, g of n exists. It's well defined. And so the next thing we want to do is prove that this function g grows really, really fast. And to make this precise, we'll define a family of functions called the fast-growing functions. It'll actually take a little bit of work to define this family because they really do grow very, very fast. But what we'll prove is that this function g grows even faster, that g is faster than any of these fast-growing functions we're going to write down. And what I really want to get at is unprovability. Goodstein's theorem is true, but it isn't provable in P&O arithmetic. P&O arithmetic is a standard formal system of axioms for the natural numbers. It can prove a lot. Gödel's theorem says there must be some things P&O arithmetic can't prove, and Goodstein's theorem is a concrete example of a true theorem that can't be proven in P&O arithmetic. We'll define what P&O arithmetic is. We'll get some idea that there are a lot of things P&O arithmetic really can prove, that it is a powerful system of axioms. And then we'll turn to proving that P&O arithmetic can't prove Goodstein's theorem. And this will tie in with what we've already done, because what we'll actually show is that the problem is this function g grows too quickly. We'll show that when a function grows as quickly as Goodstein's function does, P&O arithmetic can't prove that the function exists. And to prove this is where some ideas from proof theory will come in. We'll have to show that whenever we prove something in P&O arithmetic, the proof has a certain structure, a certain shape, and this shape can't grow too quickly. And so in particular, there isn't enough space in a P&O arithmetic proof to fit a proof of Goodstein's theorem.